This is a bowl of chocolate. So long as I keep it still, all the chocolate in the bowl stays in the same state. Now classically, this is a stationary point of the system, or probably even a stable one, and quantum mechanically, everything being in the same state for some time means they're in an energy eigenstate. Now if I start moving the bowl, I'm changing the Hamiltonian. So suddenly, quantum mechanically, I wouldn't be in an eigenstate at all. And indeed, I'm not in the same stationary point either. But if I move slowly enough, there's obviously something about this state that isn't changing. The positions of all the bits of chocolate in here are different, but they bear the same relationship to the bowl that they always had. In quantum mechanics, this also happens. It's called the adiabatic theorem. When a Hamiltonian is changed sufficiently slowly, if the system starts off in an eigenstate of the original system, then it stays in the same eigenstate of the changed system. So let's look at a quantum simulation. What we have here is we have a harmonic potential, just a quadratic potential, and as we know the ground state of that is a Gaussian. And what we have here is the strength of the potential in A and B and the position of it in x v naught. And then over here we have the simulation, which is going to be dynamic. So we've got the potential here in this light white, and we have in this solid white here we have the wave function itself, and it's completely real initially, and so there's a blue line under that white line which gives you the real part, and this red line is the imaginary part. Now if we evolve this in time, you can see that the real and imaginary part are just rotating around, but the overall intensity, this is the mod squared of the wave function, doesn't change. Okay, we can stop that, start again. Now what I'm going to do is I'm going to change this Hamiltonian. So we could, if we wanted, very carefully try and move this over here. And you can see that the wave function hasn't changed very much. You can see it's got a very slight oscillation from left to right because I moved it quite slowly. But supposing I put it back kind of violently, you'll see it is no longer in an eigenstate. So it hasn't gone into the eigenstate. Let's stop all that, reset everything. And what we're going to do is we're going to show that not only can you change the position of the trap. Now that Hamiltonian was changing quite dramatically. If we look at the potential at one point here, it was going from some very high value up to some incredibly high value. So the potential was changing a lot, but you saw that it wasn't changing shape. Let's try it when it's changing shape. So we'll make things go again. And now we're going to try changing the shape. So we're going to make it stronger. Now if we make it stronger, the actual shape of the ground state is going to change. It'll still be a Gaussian, in fact. And you can see that I've made it quite a lot stronger now, and it's almost in the Gaussian. It's got that little wobble, which means it has a little bit of some of the excited state in it, but most of it is still in the Gaussian. And it's not the same Gaussian it was before, it's the new Gaussian. Now, if we were to change that potential to add completely different elements, the ground state's not going to look like a Gaussian at all. It's going to look like something quite exotic. But if we move it slowly enough, we could expect that would eventually look exactly like the new ground state. And if I take this, and it doesn't just work for ground states, it also works if you start in an excited state. And I'm going to take it and I'm going to drop it kind of violently. And you can see there it is nothing like in the new ground state. So the ground state of this new potential is a Gaussian, but is completely the wrong shape, and you can see that it's now oscillating, so it must have components of many excited states in it. That's what happens if you move fast. But if you move slow, and that's the adiabatic theorem, then you expect things to stay in the same eigenstate they were in before. Now I've used the phrase slowly enough several times over this lecture, and the key question that should be clanging in your brain is, of course, slow enough with respect to what? So I want you to have a think and see if you can come up with the time scale that you have to move slower than in order for the adiabatic theorem to work.